In Module 11, Section 2, we will discuss rational exponents. So far, we have only worked with integer exponents, but in this section, we will extend exponents to rational numbers as a shorthand notation using radicals. The same rules that applied before will apply to exponents in this section. If n is a positive integer greater than 1, and the nth root of a is a real number, then we can rewrite the nth root of a as a to the 1 over n power, and vice versa. Let's try to do that in a few examples. So here we want to use radical notation to rewrite each expression and then simplify if possible. We start with 81 to the 1/4 power, so using the definition from the last page, we can rewrite this as the 4th root of 81. Now remember, we can make a factor tree or find the prime factorization of the number underneath the root. Use the index to find the number of identical factors that are needed to form a group, and then pull those groups of numbers out from underneath the radical. So we take 81, and its prime factorization is 3 times 3 times 3 times 3. The index indicates any groups of 4 identical factors, and we just happen to have 4 identical factors. So the 4th root of 81 is 3. Let's try the same thing with the next example. 64 to the 1/3 power can be rewritten as the cube root of 64. The prime factorization of 64 is 2 times 32, which is 2 times 16, 2 times 8, 2 times 4, 2 times 2. The index 3 indicates many groups of 3 identical factors. So I have 3 2's, but I also have another group of 3 2's. Whenever we have more than one group, we multiply each group together. So the first group represents 1 2. The second group represents another 2. 2 times 2 is 4. The cube root of 64 is 4. We can use the same notation to simplify the last example. X to the 1/4 power can be rewritten as the 4th root of x. This can't be simplified, so the 4th root of x will just be the answer. Let's try it again with a few more examples. Use radical notation to rewrite each expression and simplify if possible. So we start with a negative 16 raised to the 1/2 power. So we write this as the square root. Now, the only time we don't write the index is if it's a 2. So if you never see an index on the outside of the radical sign, it means it's a square root and the index is 2. So the square root of negative 16, but just like we talked about in the previous section, we cannot take square roots of negative numbers and have a real answer. And right now we're not equipped for that, so we say this is a not real solution. Let's go down to part E. I'm going to take 32x to the 10th, raise it to the 1/5 power, which is the same thing as finding the 5th root of 32x to the 10th. We write the prime factorization of 32, 2 times 16, which is 2 times 8, 2 times 4, 2 times 2. And the index indicates we need 5 identical factors to form a group. We happen to have 5 identical factors. So the 32 breaks down into 2. Let's go to the variable now. The 5th root of x to the 10th, remember what we did before, we found the quotient of the exponent and the index. So we take 10 divided by 5 is 2, and that's how many factors of x will come out from underneath the 5th root. So 2 factors, or x squared, with no remainder. Let's try another example. We want to use radical notation to rewrite each expression and simplify if possible. Here we have 16x to the 7th, all raised to the 1/3 power. So we can rewrite this as the cube root of 16x to the 7th. Just like in the previous examples, let's write our prime factorizations and do our long division for our variables. So 16 is 2 times 8, which is 2 times 4, which is 2 times 2. We have 4 factors of 2. And our index indicates we need 3 identical factors to form a group. So 3 of our factors form a group, and this is the first time we've seen this so far. We have 1 leftover factor. So in the next line, I get to bring the group to the outside, so I have a 2 on the outside, but I have a 2 that's stuck underneath because it didn't form a group. Let's go to the variables. We do long division with our exponent and our index. So we have 7 divided by 3. 3 goes into 7 twice. 3 times 2 is 6. We subtract, and we have a remainder of 1. Let's talk about what the remainder means. First, the quotient 2 means we pull 2 factors of x outside of the root, or x squared. The remainder means we have 1 factor of x still stuck underneath the cube root. So our answer is 2x squared times the cube root of 2x. Here's another definition. If m and n are positive integers greater than 1 with m over n in simplest form, then we can have a number raised to the m over n power. The number on bottom still is our index on our radical, and the number on top is the exponent, as long as the nth root of a is a real number. So let's try a couple of examples. We want to use radical notation to rewrite each expression and then simplify if possible. So here we have 4 raised to the 3 halves. The number on bottom, indicated in blue here, is the index. Whenever the index is 2, we write square root. So square root of 4, that will all be raised to the top number, to the 3rd power. So we start by taking the square root. The square root of 4 is 2. 2 to the 3rd power is 8. Let's try another example. In the next example, we have negative 8 to the 4/3 power. The number in the denominator of the exponent is the index, so the cube root of negative 8, all raised to the 4th power. From before, the cube root of negative 8 is negative 2. Negative 2 to the 4th power, now that means we have 4 factors of negative 2. And when we multiply all of those together, that will give you a positive 16. We can also do this with algebraic expressions. Here we have 3x plus 7, all raised to the 7/3 power. The number on bottom indicates the index, so the cube root of 3x plus 7, all raised to the 7th power. And that can't be reduced any further. It's just another way to rewrite the expression. To complete our definitions, we have one more, and this includes the negative rational exponents. And this definition is actually exactly the same as the definition we would have seen with integer exponents. If we have a negative fractional exponent, to write that as a positive fractional exponent, we take the entire term and write it under 1, or I made this adjustment to the last definition we saw in Module 5. If it's negative in the denominator, you move it to the top, write it in the numerator with a positive exponent. You can think of this definition either way. So now let's use that definition to write each expression with a positive exponent, and then we will simplify. So if we have 64 to the negative 2/3, we rewrite that as 1 over 64 to the positive 2/3. Now let's use our other definitions to simplify. So this equals 1 over the cube root, because the number on bottom tells us the root, of 64, all raised to the 2nd power. The cube root of 64, if you remember that list of cubes I made before, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. So the cube root of 64 is 4. This becomes 1 over 4 squared. 4 squared is 16. So the answer is 1 over 16. You have to have a positive exponent before we can go through the simplification process. Here we have another example. In this example, we have negative 16, all raised to the negative 5/4 power. But because negative 16 isn't in parentheses, that exponent doesn't apply to the negative. The exponent only applies to the 16. And so when we rewrite this, the negative actually stays in the numerator, or negative 1 over 16 to the positive 5/4 power. We now use our other rules. This becomes negative 1 over the number in the bottom of our exponent. The denominator of our exponent tells us the kind of root we have. 4th root of 16, all raised. The top number was the exponent to the 5th power. So we can take the prime factorization of 16, 2 times 2 times 2 times 2. The index indicates that we need 4 identical factors, and that's exactly what we have. So the 4th root of 16 is just 2, negative 1 over 2 to the 5th. And if you work out 2 to the 5th, you will get 32. So the answer is negative 1 over 32. This is a summary of the exponent rules, and these rules apply to fractional exponents, integer exponents, any exponents that you will see in this class. So let's use those properties of exponents to simplify these expressions. First, we have x to the 1/2 times x to the 1/3. And we would use the product rule. If we are multiplying, we add the exponents and write the base 1 time. So we have x raised to the 1/2 plus 1/3. Before we can add those fractions together, we have to have common denominators. The common denominator of 2 and 3 is 6. To get a 6, we multiply the first fraction by 3 over 3. the second fraction by 2 over 2. And that gives us x raised to the 3 over 6 plus 2 over 6, which would be x to the 5 over 6 power. And it's okay to leave it in exponential form for these problems, unless otherwise stated. Let's try the next example. 7 to the 1/3 power over 7 to the 4/3 power. Hopefully you remember our little trick to the quotient rule, and that was to find the largest exponent and then write all of our base in that location. It wasn't always the numerator. Sometimes it was the numerator, sometimes it was the denominator. Because here our exponents have the same denominator, 1/3 and 4/3, we know that 4/3 is larger than 1/3, so all of our 7s will move down to the denominator. We will subtract the largest denominator minus the smallest. 4 over 3 minus 1 over 3 is 3 over 3. We need a placeholder of 1 in the numerator. 3 over 3 is just 1, so this becomes 1 over 7 to the first power, or just 1 over 7. And let's try another example. Example C, y to the negative 4 over 7 times y to the 6 over 7. We can move the first term down to the denominator and then work it out. But since we're already multiplying, we can use the product rule and just add the exponents. So this will become y to the negative 4 over 7 plus 6 over 7. We have a common denominator, so that becomes y to the 2 over 7. And that's the simplified result. Let's try another example. Again, we want to use the properties of exponents to simplify. We have 32 to the 1/5 times x to the 2/3, all raised to the 3rd power. Remember, if we have an exponent on the outside of a product, we take that exponent to both pieces. So this becomes 32 to the 1/5, all raised to the 3rd power, times x to the 2/3, all raised to the 3rd power. Now, for each of these expressions, whenever you have an exponent raised to an exponent or multiple exponents, you're going to multiply. So let's change these exponents of 3 to 3 over 1. When we multiply, that will give us 32 to the 3 over 5 times x to the 6 over 3. We reduce if we can. And when we have constants, the way we reduce is we write it as a radical, reduce, and then change it back to an exponent if we need to. So we write this as the 5th root of 32, all raised to the 3rd power, times 6 over 3 is 2, so this becomes x squared. The 5th root of 32, we've done this before, but let's write the prime factorization of 32. 2 times 2 times 2 times 2 times 2. The index says we need 5 identical factors, and that's what we have. So the 5th root of 32 is 2. That gives us 2 cubed times x squared. 2 cubed is 8. So this simplifies to 8x squared. Let's try another example. Again, we want to use the properties of exponents to simplify. So we have a to the 1/4 times a to the negative 1/2 all over a to the 2/3. One thing we can do right away is just get a common denominator with each fractional exponent. We have denominators of 2, 3, and 4, and so we would find that the LCD is 12. So we multiply each fraction accordingly to change the denominators to 12. And that would give us a to the 1/4 times 3 over 3 times a to the negative 1/2 times 6 over 6 all over a to the 2/3 times 4 over 4. If we rewrite these equivalent fractions, that will give us a to the 3/12 times a to the negative 6/12, all divided by a to the 8/12. So with the a's that are beside one another in the numerator, we will add those exponents. 3 over 12 plus negative 6 over 12 is a negative 3 over 12. So a to the negative 3 over 12, all divided by a to the 8 over 12. Now remember, as long as we have the common denominator with the exponents, we're going to look at the larger exponent and move all of our a's that direction. 8 is larger than negative 3, so all of our a's will move down to the denominator. We then take the larger exponent minus the smaller exponent. 8 over 12 minus negative 3 over 12. Let me just write that down so you can see it. 8 over 12 minus negative 3 over 12. That's the same thing as 8 over 12 plus 3 over 12, which would be 11 over 12 as the exponent. Make sure to put your placeholder of 1 in the numerator, and we are finished with that problem. Here we have a few different types of problems. We want to use rational exponents to simplify. What we are trying to do is rewrite the expression with a smaller index. Once we go from radical form to exponential form, we reduce and we rewrite it in radical form. So for A, we rewrite this as x, the exponent on the inside goes on top, over, the index on the outside goes on bottom. We can reduce 4 over 8 to 1/2. And once we've reduced, we're going to rewrite it in radical notation. Remember, the number on bottom tells us what kind of root we have. It's a square root of x to the first power, or just the square root of x. Now, part B will be a little bit tricky unless you rewrite 25 in the smallest terms that it can be rewritten. We know that 25 is 5 times 5. We can write that as 5 squared. So let's start the problem by writing the 6th root, not of 25, but of 5 squared. Using our radical to exponential fraction rule, this becomes 5 to the 2 over 6. 2 over 6 reduces to 1 over 3. And then we can rewrite this as the cube root of 5. Let's try to do the same thing with the next two examples. We want to use rational exponents to write as a single radical expression. So we're going to go from radical expressions to exponents, combine the two exponents together, and then go back to radical expression. So the square root, using the rule that was introduced at the very beginning of this section or the last section, we rewrite this as the x to the 1/2 power times the 4th root of x is x to the 1/4 power. We get common denominators, so we need a 4 in the first denominator. Once you get a common denominator, it will become x to the 2 over 4 times x to the 1 over 4, which is x to the 3 over 4. But we don't want to leave it in this form. We're going to change x to the 3/4. The number on bottom tells us the index, so the 4th root of x to the 3rd power. We can do the same thing with the numbers in the next expression. 5. The cube root of 5 is 5 to the 1/3 times the square root of 2 is 2 to the 1/2. We get common denominators with 1/3 and 1/2. The LCD is 6, so we multiply by 2 over 2 in the first fraction, 3 over 3 in the second fraction, and that gives us 2 over 6 plus 3 over 6. But we're not going to add these together because the 5 and the 2 aren't the same. But we were able to find common denominators. So we have 5 to the 2 over 6 times 2 to the 3 over 6. And we can rewrite this as 5 squared times 2 cubed, all raised to the 1/6 power. We're just going to throw the denominator on the outside. The 1/6 power tells us we have a 6th root. 5 squared is 25. 2 cubed is 8. 25 times 8 is 200.